let's take an algebraic look at the same identity that we have when choosing with repetition and choosing without repetition. For without repetition, we can think of this set, this K set, as a sequence of numbers taken in order. So 1, of course, is the smallest number that we could take, and our smallest number has to be at least that big, and then we have to take a different number, and then so on and so forth, up until the last number, which we know is at most this big, n plus k minus 1. So this is a K set chosen from the numbers 1 up to n minus k plus 1. It's the number of sequences A that satisfy this. And now let's think about what happens in the green case. In the green case, we've got the number 1, and our first number, our smallest number, has to be at least that big. But the next number could be the same, and the next number could be the same, and so on. So we get a weak inequality. And now the biggest number that we could have is n. So this is choosing with repetition between the numbers 1 to n. Now, how do we get a bijection between these two sets? That'll give us another bijective proof of this identity. Well, our clue comes from looking up here at the top. We know that A1, well, it's at least 1. So since this inequality is strict, A2 is at least 2. And then, of course, AK, following through, is at least K. So one common thing we do in sequences is called compression, and this is a very common technique to take us from strict inequalities to weak inequalities. You look at what's the compression factor that I can take. And so the bijection that we're going to have from the blue set to the red set is we're going to define BI to be AI minus the biggest amount we know we can subtract off, which is I minus 1. So we subtract nothing from A1, 1 from A2, and so on to K minus 1 from AK. And now let's just check that we get a weak inequality. Well, since we know that AI is at least I, it follows that BI is greater than or equal to I minus 1, which is 1. So the BI's are non-negative, they're positive integers. That's good. Now let's check our final condition that translates. Well, we have AK is less than or equal to n plus k minus 1. So that means that BK is less than or equal to, again, we're going to replace here. This is going to be n plus k minus 1 minus k minus 1. And so this is equal to n. And then, of course, this is injective, and we can reverse it. It's pretty easy to see how to go backward from the one to the other. And so this gives us another way to prove this theorem. And in fact, this proof of the theorem gives us a way to think about the generating function. So remember that we had the binomial theorem, which is 1 plus x to the n is equal to the sum from 0 to infinity of n choose k x to the k. And what we said was that this is sort of like here, not taking the element, so don't take k, don't take I in your set, and here this corresponded to take I. And that's our combinatorial interpretation. So now when we think about how to do this generating function, so now what we want to do is come up with what happens if we change this and say we want the sum of the multi-choosing n choose k. Now notice this one's not going to die, right? I could have 4 types of elements and I could still choose 100 of them because I can choose with repetition. So this is really using the fact that we're going to have an infinite series here. Using the same analogy, what am I doing? So it's still going to be something to the n, but it's going to be something that's a lot more difficult. We can think about it as whatever my first choice is, I can take it, not take it, or I can take it once, or I can take it twice, or 3 times, or 4 times, as many times as I want, arbitrarily many. And then the second thing in my list, the number 2, I could take it once, or twice, or 3 times, and so on and so forth. And you just keep going for however many things that you have. And of course, if n, you could either not take it once, take it twice, and so on. So what we get is that the generating function is 1 plus x squared plus n times, which of course this is 1 over 1 minus x to the n. So we can see a nice relationship between the generating polynomial that we got here, which is in fact a polynomial, and the generating function that we get here. And again, we'll maybe emphasize here, this first term you can think of as no 1, and this is 1, 1, and this is 2 1s, and so on. So you're taking each term as many times as you want, and that's how we can get the generating function for choosing with repetition. And now an interesting thing to think about is how these two generating functions are related to one another and what this theorem tells us about that. So if we're going to look at the generating function and we think to ourselves, well, how does this generating function relate to that generating function? We have a nice corollary. Maybe I'll write it in a fun color. We're going to get an identity as a corollary. And the corollary is that choosing with repetition is the same thing as taking an alternating sum of choosing without repetition when you have a negative number of options. And the proof of this fact comes just from the generating function. How do we make this look like this? We need to put minus n into the numerator, and we need to replace x with minus x, and that's going to pull out our minus 1 to the k. So this is just follows from the generating function. We get this interesting combinatorial reciprocity for multi-set selection. And that'll be something that comes up again and again.